In the name of God, the most gracious, the most merciful, peace be upon you and God's blessing. We are going to have a look at practice problem number 1 from the Unified Design of Steel Structures Handbook. I am going to modify the practice problem to include metric bolt sizes. First, there is a table showing the difference between the sizes of bolts based on inches and the metric bolts. We can see that the smallest size is 1/2 inch, which had a diameter in millimeter equals 12.70 millimeter. The 5/8 inch bolt has a bolt size of 15.88 millimeter. After the 5/8 inch bolts come the M16, which has a diameter of 16 mm. The next bolt is 3/4 inch, which has a diameter of 19.05 millimeter and an area of 285 mm square. M20 has a diameter of 20 millimeter and an area of 314 mm square. While for M22, its diameter is 22 millimeter and the area is 380 millimeter square. A 7/8 inch bolt has a bolt size of 22.23 millimeter. After the 7/8 inch bolt comes M24, which has a diameter of 24 millimeter. M27 bolt has a bigger diameter than 1 inch diameter. From the next slide, we will find the conversion factor for KSI to Newton per millimeter square. We start from our information in physics that 1 pound force acts on 1 pound mass with an acceleration of 9.800 meter per second square, while 1 kilogram force acts on 1 Newton with an acceleration of 9.8066 meter per second square. There is a relation between pound mass and 1 kilogram mass, that 1 pound mass is 0.4536 kilogram mass. Then the 1 pound force equals 0.4536 kilogram force. The 1 pound force will be equal to 0.4536 multiplied by 9.8066, or simply 4.4485 Newton. We return to 1 KSI, which is 1 kilopound per inch square. 1 inch square is equal to 645.2 millimeter square. We can derive the expression that 1 KSI equals 6.89476 Newton per millimeter square. In the next slide, we can review the stress values in table J3.2 against the imperial stress and find out the corresponding values in Newton per millimeter square or megapascal. For the A307 bolts, the nominal tensile strength of 45 KSI is multiplied by 6.89476 to get the value in Newton per millimeter square, which will be equal to 310.26 Newton per millimeter square, rounded to 310 Newton per millimeter square as in table. For the same A307 bolt group, the nominal shear strength is 27 KSI multiplied by the CF, which stands for the conversion factor. We get the value of 186 Newton per millimeter square. For group A325N bolt, the nominal tensile strength of 90 KSI is multiplied by 6.89476 to get the value in Newton per millimeter square, which will be equal to 620 Newton per millimeter square after rounding. For the same A325N, the nominal shear strength is 54 KSI multiplied by the CF, which stands for the conversion factor. We get the value of 372 Newton per millimeter square. For A325X bolts, the nominal shear strength of 68 KSI is multiplied by 6.89476 to get the value in Newton per millimeter square, which will be equal to 469 Newton per millimeter square or 469 megapascal after rounding. For group B, for instance A490N, the nominal shear strength is 68 KSI multiplied by the CF, which stands for the conversion factor. We get the value of 469 Newton per millimeter square after rounding. For group B, for instance A49X, the nominal shear strength is 84 KSI multiplied by CF. We get the value of 579 Newton per millimeter square after rounding. To see our practice problem number 1, we move to the next slide. It is required to develop a table for the nominal shear strength for A325N for 5/8 inch, 3/4 inch, 7/8 inch, and 1 inch. I have modified the problem to develop a table for the nominal shear strength for A325N for M16, M20, M24, and M27. These metric bolts are slightly higher in the area, as we have discussed earlier, than the bolts in inches. We start with the first type, which is A325N. N indicates that the thread is included in the shear plane. We have a nominal shear strength value, capital F sub NV, equal to 372 N per millimeter square. We will not use any design parameters, phi or omega, because it is required to derive the values in nominal shear strength. In the next slide, we start with the first bolt with a diameter of M16. The nominal shear strength is 372 Newton per millimeter square, and the area of M16 is equal to 201 mm square. We could divide the F sub NV value by 1000 to convert the value to kilonewton per millimeter square. Multiply 0.372 by 201. The nominal shear value for the M16 bolt is equal to 74.77 kilonewton. To get the nominal shear strength for the second bolt M20, multiply F sub NV by area. The area of M20 is equal to 314 millimeter square. Multiply 0.372 by 314. The nominal shear value for M20 bolt is equal to 116.81 kilonewton. Next, we will proceed to the third bolt, which is with the diameter of 24 millimeter, or M24. The area of M24 is equal to 452 millimeter square. Multiply 0.372 by 452. The nominal shear value for the M24 bolt is equal to 168.14 kilonewton. In the next slide, we have a bolt with a diameter of M27. The area of M27 is equal to 573 millimeter square. Multiply 0.372 by 573. The nominal shear value for the M27 bolt is equal to 213.16 kilonewton. We can develop a small Excel table for the previous diameters in millimeters squared, and later find the LRFD and ASD values for design shear and allowable shear for bolts. Thanks a lot, and see you in the next video. God bless you all.